Alright, this particular video is designed to draw a connection between right triangle trigonometry and trigonometry as we perceive it around the unit circle. First and most important idea is we are working with a unit circle, and why that's important essentially is because we can make a right triangle with any rotation that we make around the unit circle, and when we do, that right triangle will always have a hypotenuse of 1 unit long. The reason that's significant is if we were to indicate that our central angle represents the Greek letter theta, which is just a variable. We used up all the other variables, so we had to start stealing from the Greek alphabet. That's the capital letter T anyway, but enough trivia. If this is the angle theta, then we can identify the opposite side from theta, which, if I'm going to stick with my scheme here, there we go, the opposite side, and then we are going to have the adjacent side, and of course we have the hypotenuse. But because we're working in the unit circle, we can always define the hypotenuse as 1. Therefore, if we were to look at the sine of theta, we can see that that ratio is a comparison of the length of the opposite side divided by the length of the hypotenuse, which we know to be 1. Therefore, the length of the opposite side, you down with OPP, is equal to the sine of theta. That may not seem significant to many people, but when working with trigonometry and triangles, we always had to make relative comparisons. We had to look at the length of this side and describe how it compares to the length of this side right here. But now, because the length of the red side, the hypotenuse, is always fixed at 1, we don't have to look at the relative comparisons of these two sides. We simply need to focus on the length of just the opposite leg itself. So in other words, we've cleaned up trigonometry so that the length of the opposite leg is the sine of the angle. They're synonyms. So what we have is a visualization, a complete visualization of the sine of theta. This length right here is the sine of theta. Similarly, the cosine of theta is going to be represented by this length right here. However long that is, that's going to be adjacent over hypotenuse, which we know the hypotenuse is 1. Therefore, the length of the adjacent is the cosine of theta. That presents the latest truism. If we rotate anywhere on this unit circle, we are going to have a point x and a point y, and because the hypotenuse of this right triangle is always 1, we can now say that the cosine of theta is always going to be your x coordinate, and the sine of theta is always going to be your y coordinate. Now, of course, if I was being, a little bit more prepared, I would have done color coding. I would have said sine of theta like this, and then I would have shown cosine of theta like this in purple, which it already is. And then you'd be like, ew, awesome. Anyway, I'm sorry, I'm tired. Let's see. So that means the implications for trigonometry is that if we rotate into the second quadrant, here for example is an illustration of rotating 2 radians. Well, what's happened now is suddenly we have a point in the second quadrant. To get there, we have to go in the negative direction horizontally, but the positive direction vertically. If we were to look at the coordinates of this point right here, the coordinates are telling us that we had to go in the negative direction about 0.4, or almost a half a radius, 40% of a radius if you will, and then we had to go up 0.9, which is almost a whole radius length. If you look at the circle, we'll remove this point for a second. If you look at the circle, this length here is 1, and when we rotate 2 radians, our vertical height, or sine, is already very, very close to 1. It's at 90%. So we'll show you that. There it is. It's about 90% of the length of the radius. So as a result, we can focus on a couple of things. The first is, in black, we know a equals 2 represents our rotation. This time we'll call it theta equals 2 radians. As a result, I am now able to say that the cosine of 2 radians is equal to negative 0.416. And I could further say that the sine, which is green, of a rotation of 2 radians is going to be equal to 0.909, and that's again evidenced by this coordinate right here. Once again, when I see the sine, it opens up my mind. When I see the sine, I'm talking about looking at this length and its positivity that is relative to the x-axis. It's positive 90% of the length of one radius. And when I look at the cosine right here, I'm keeping my attention to the x, or horizontal movement. I recognize it's in the negative direction and it's less than halfway across the radius, or about 40%. So hopefully this will help you understand what's meant when we talk about trigonometry. The beauty part is we can move around and around the circle and we can watch the sines and cosines change. Let me slow that down a little bit. Nice and easy there. Calm down, big guy. So here again, as I continue to rotate round and round and round, we can see what happens to the cosine. That's this x value. It goes all the way to -1, and then it rotates back to 0 again, and then it goes all the way to +1. We're rotating backwards right now because that's what my computer decided to do, and it's going to rotate again forwards once it's done. But here we see again the cosine just keeps going back and forth between -1 and +1. Here it's at 0. Then we can look at the y-coordinates, the sines. Now it's at 0. Then the y-coordinate goes all the way up to 1. So these are sines. Now the sine is 0. Now the sine is going back down to -1, and so on. I hope this was informative. Again, you'll have this simulation. I'll send it to you, and you can use it anytime to help you understand what's happening when you do trig with pencil and paper. Enjoy.